Our video tutorial is about law of conservation of energy. This is the continuation of our previous video. This includes Newton's law of motion and projectile motion. These are the equations that we are going to use. For example, problem number 1. A rock is tied to a cord and the other end of the cord is held fixed. The rock is given an initial tangential velocity that causes it to rotate in a vertical circle. Prove that the tension in the cord at the lowest point exceeds that at the highest point by 6 times the weight of the rock. So this is the problem. The rock is made to rotate in a vertical circle. We are going to prove that T sub B minus T sub A is equal to 6 times the weight of the rock. From energy conservation principle, the sum of the kinetic and potential energy at point A and point B are equal. So at point A, the kinetic energy is 1/2 mB sub A is square plus its potential energy, mg times the height. The height is this distance, which is twice the radius. Its kinetic energy at point B is 1/2 mB square. Its potential energy at point B is 0 since point B is our reference level. Simplify and cancelling out common factor in each of the term. Then multiply the whole equation by 2. Then interchange the left and right member of the equation, solving for B sub B square. So this is our equation number 1. For our free body diagram, at point A, the forces acting on the rock, tension downward, tension exerted by the rope downward, the weight of the rock downward, the acceleration or the central acceleration directed towards the center. At point B, the forces are tension in the cord upward, the weight downward, and the central acceleration towards the center, which is upward. From Newton's second law, the summation of all forces along the y-axis is equal to mass times acceleration. At point A, the central acceleration, our acceleration is central acceleration since the body is moving in a circle, which is equal to the square of the speed divided by the radius. So at point A, tension T sub A is directed downwards, negative. The weight is directed downward, is negative also. The acceleration is towards the center, which is downward. So it is negative. Multiplying the whole equation by positive 1, so negative becomes positive. And this is our equation number 2. At point B, T sub B upward positive minus the weight downward equals mass times the acceleration, which is upward positive. Then simplifying the equation, solving for T sub B, transfer negative mg to the right becomes positive. So this is our equation number 3. From equation number 2, interchanging the left and right side of the equation so that we express mb sub e square over r equal to T sub A plus mg, our equation 2. We just rewrite equation 2. Then from this equation, substitute equation 1 and equation 3. So mb sub b square is replaced by this expression. Then distribute m in its term. Then combine similar terms. mg and 4mg becomes 5mg. This is our equation number 4. Substitute equation 2 in equation 4. So this term is replaced with this expression T sub A plus mg. Then combine similar terms. 5 mg and mg are similar, so that becomes 6 mg. transfer T sub E to the left side of the equation. This equation means that T sub B exceeds T sub A by 6 times the weight of the rock. Problem number 2. A small block of ice with mass 0.12 kg is placed against a horizontal compressed spring mounted on a horizontal tabletop that is 1.9 meters above the floor. The spring has a force constant K equal to 2,940 newtons per meter and is initially compressed 0.045 meter. The spring is released and the block slides along the table, goes off the edge and travels to the floor. If there is negligible friction between the ice and the table, what is the speed of the block of ice when it reaches the floor? So here is our problem. This is a block of ice placed against this compressed spring and it is released from conservation energy principle. Let us consider point 1 and 2. The sum of the kinetic and potential energy at point 1 and 2 are equal. At point 1, the kinetic energy is 0 since it is at rest. At point 2, its potential energy is 0 since the height of the block at point 2 is 0 with respect to point 1. At point 1, it has elastic potential energy which is equal to 1/2 kx squared. At point 2, its kinetic energy is 1/2 mv sub 2 squared. Substituting the value of the force constant K and x the length of the compressed spring, x the length where the spring is being compressed, the mass of the block of ice. So simplify x squared and solve for b squared. Extract the square root on both sides. So at point 2, its speed is 7.04 meters per second. Next, let us consider the motion of the block from point 2 to point 3. And again, according to energy conservation principle, the sum of kinetic and potential energy at point 2 and point 3 are equal. Considering the motion from point 2 to point 3, our reference level is point 3. So at point 3, its potential energy is 0. At point 2, its kinetic energy is 1/2 mv sub 2 squared, and its height, it has potential energy because our reference level is point 3, so it has potential energy mg times h, and its kinetic energy at point 3 is 1/2 mv sub 3 squared. Cancelling out the common factor on each term of the equation, then substitute b sub 2 squared. This is b sub 2 squared, this value, and acceleration due to gravity g 9.8, height 1.9. So simplifying and combining terms and multiply the whole equation by 2. So b sub 3 squared is equal to 86.852. Extracting the square root on both sides. So b sub 3, or the speed at point 3, is equal to 9.32 meters per second. We will consider solution 2. Let us consider the motion of the block of ice from point 2 to point 3. At point 2, previously its speed is 7.04 meters per second. Its velocity is directed horizontally, so b sub x. Y component of its velocity is 0 because initially at point 2, the block of ice is moving horizontally. At point 3, this is the horizontal and vertical component of its velocity. its x component is constant because there is no force along the x direction, only along the y direction, the acceleration due to gravity. So we are going to solve for the final speed at this point. So from uniformly accelerated motion, this equation b sub y final square is equal to b sub y initial square plus 2 times acceleration due to gravity times the height. At point 2, its initial vertical component of its velocity is 0. Its acceleration due to gravity is negative 9.8. The height, considering point 2 as the origin, downward is negative. Simplifying and extracting the square root on both sides of the equation, so the y component of the velocity at this point is 6.102. With this x and y component, we can solve for the value of v using Pythagorean theorem. So substituting the x and y component of the velocity, simplify and extract the square root on both sides. So still at point 3, the final velocity is the same as in our solution 1, 9.32 meters per second. Problem number 3, a block with mass 0.5 kg is forced against a horizontal spring of negligible mass, compressing the spring a distance of 0.20 meter. When released, the block moves on horizontal tabletop for 1.0 meter before coming to rest. The spring constant K is 100 newtons per meter. What is the coefficient of kinetic friction U sub K between the block and the table? So here is our problem. This is a block compressing the spring a distance of 0.20 meter. Then when released, the block moves to the right and it comes to rest at point 2. So from energy conservation principle, we have here kinetic energy at point 1, the elastic potential energy at point 1, and other work which is negative. It is negative due to the force of kinetic friction that opposes the motion of the block in the process reducing its energy. Then at point 2, it has kinetic and potential energy, and their values. At point 1, its kinetic energy is 0 since it is at rest. Its elastic potential energy is 1/2 K x squared. Then the other work, which is negative, is force times distance. At point 2, the block is at rest, so it is 0, and its height at point 2 is 0. So the value of kinetic energy and potential energy at point 2 is 0. So simplifying and substituting the force of kinetic friction, which is U sub K times the normal force. The normal force is equal to its weight, which is mass times acceleration due to gravity. Substituting the value of K, which is 100, x is 0.20, mass is 0.5, g, acceleration due to gravity is 9.8, s is 1 meter. Simplifying and solving for U sub K in this equation. So U sub K is equal to 2 divided by 4.9, which is equal to 0.408. So the coefficient of kinetic friction is 0.408. Problem number 4. A wooden block with mass 2 kilograms is placed against a compressed spring at the bottom of an incline of slope 37 degrees, point A. When the spring is released, it projects the block up the incline. At point B, a distance of 6 meters up the incline from point A, the block has a velocity with magnitude 4 meters per second, directed up the incline. The coefficient of kinetic friction between the block and the incline is U sub K equal to 0.5. Calculate the amount of potential energy that was initially stored in the spring. So this is our problem. This is a block compressing the spring. When released, it moves to point B up the inclined plane, and at point B it has velocity 4 meters per second. For the free body diagram, we have here the normal force, the weight directly downward, the component of the weight perpendicular to the plane, and the component of the weight parallel to the plane. So from energy conservation principle, at point A, we have kinetic energy, elastic potential energy, and the negative work done by the kinetic friction on the block as it moves upward. So the work done is negative. At point B, it's kinetic and potential energy. For the value of each term, at point A, its kinetic energy is 0 since it is at rest. And its elastic potential energy is what we are going to solve for. It is unknown. The other work is equal to force times distance. At point B, its kinetic energy is 1/2 mv square, and its potential energy is the weight times the height. The height is this one. It's sub B. From this triangle, the sine of 37 degrees is equal to opposite h sub B over the hypotenuse, 6 meters. So cross multiply, solving for h sub B, it is equal to 6 times sine of 37 degrees. So substituting it here in h sub B and substituting the values, U sub A, the elastic potential energy is unknown. The kinetic friction is equal to U sub K times the normal force. M is 2. At point B, its velocity is 4. Its mass is 2. Acceleration due to gravity is 9.8, and the height at point B is 6 times sine of 37 degrees. Simplify this one. The normal force from our free body diagram is equal to weight times cosine of 37 degrees, but the weight is equal to mass times acceleration due to gravity. Add this one, then substitute the other value. U sub K is 0.5, mass is 2, G is 9.8. Simplify this term and solve for U sub A in this equation. Transfer this negative to the right, becomes positive, and combine. So U sub A, the stored potential energy in the spring, is equal to 134 joules. Problem number 5. A baseball is thrown from the roof of a 27.5 meter tall building with an initial velocity of magnitude 18.5 meters per second and directed toward at an angle of 37 degrees above the horizontal. A. What is the speed of the ball just before it strikes the ground? Use energy methods. B. What is the answer for part A if the initial velocity is at an angle of 37 degrees below the horizontal? So this is our problem. A baseball is thrown at this direction, 37 degrees above the horizontal, with an initial velocity of 18.5 meters per second. So we will consider the motion of the ball from point A to point B from energy conservation principle. From this triangle, let us determine the x and y component of its initial velocity. For the x component, so this is equal to 18 hypotenuse times the cosine of the angle. The hypotenuse is 18.5. So the x component is 14.775. The y component is equal to hypotenuse 18.5 times the sine of the 7 degrees is 11.134. From energy conservation principle, considering the motion of the ball from A to B, so at point A, its potential energy is 0 since our reference level is point A. At point A, its kinetic energy is 1/2 mv sub O square. At point B, its kinetic energy is 1/2 mv sub x square, and its potential energy is weight times the height h. Cancelling out common factor in each of the term, then substitute the value of the initial velocity, 18.5. B sub x is 14.775. Acceleration due to gravity, negative 9.8, and height, negative 8. Considering point B as the origin, downward is negative, so negative 8. Simplify, solving for h in this equation, so h is equal to 6.32 meters. So this height is 6.32 meters. Considering the motion of the ball from point B to point C, at point C, its potential energy is 0 since we consider the ground as the reference level. At point B, its kinetic energy is 1/2 mv sub x square. At point B, its potential energy is mg times the height, the total height. And at point C, its kinetic energy is 1/2 mv square. Cancel out common factor in each of the term. So this is the simplified form of the equation. The total height h is 33.82 meters, 6.32 plus 27.5. Substitute the value. At point B, its x component is equal to 14.775. Since the x component of the velocity of a projectile motion is constant, g is negative 9.8, h is negative 33.32 meters. Simplifying, multiply, combine similar terms, solving for b sub c, extracting the square root on both sides. So the velocity of the ball at point C is 29.7 meters per second. Letter B. Let us solve for the velocity of the ball at point B or on the ground if the ball is thrown 37 degrees below the horizontal. From energy conservation principle, at point B, its potential energy is 0 since the height is 0. We consider point B as the reference level. At point A, its kinetic energy is 1/2 mv sub A square, and its height is mgh. And at point B, its kinetic energy is 1/2 mv sub B square. Cancelling out common factor in each of the term, substitute the values. B sub A, velocity at point A is 18.5. G is negative 9.8, H is negative 27.5. Then simplify and combine similar terms. Multiply the whole equation by 2. Extracting the square root on both sides. So B sub B is equal to, or the velocity at point B is equal to 29.7 meters per second. The same as in part A. Problem number 6. In a truck loading station at a post office, a 2 kilogram package is released from rest at a point A on a track that is 1/4 of a circle of radius 1.6 meters. It slides down the track and reaches point B with a speed of 4 meters per second. From point B, it slides on a level surface a distance of 3 meters to point C where it comes to rest. A. How much work is done on the package by friction as it slides down the circular arc from A to B? What is the coefficient of kinetic friction on the horizontal surface? Okay, so here is our problem. This is a package from point A, slides down to point B of this quarter of a circle. From point B, it slides to point C. a distance of 3 meters and it comes to rest. So from energy conservation principle for letter A, considering point A to point B for the motion of the package, as it slides down from A to B, there is other work done on the package. The potential energy at point A is mg, weight, times the height. This is the height, 1.6 meter. At point A, its kinetic energy is 0 since the body starts from rest, plus the other work. At point B, its potential energy is 0. Its kinetic energy is 1/2 mb sub b squared. In letter A, it is asking for the work done on the package as it slides down from point A to point B. So the other work is unknown. So solving for W other, transfer mg to the right becomes negative. Then substitute the value, mass is 2 kilograms. At point B, its speed is 4 meters per second. Then the mass again 2. Acceleration due to gravity, negative 9.8. Height, this height, considering distance down is negative 1.6. Simplify and multiply, combine. So the work done on the package as it slides down from point A to point B is negative 15.4 joules. Letter B, what is the coefficient of kinetic friction on the horizontal surface? So from energy conservation principle, we will consider the motion of the package from B to C. So at point B, its potential energy is equal to 0. Its kinetic energy is 1/2 mb sub b squared plus other work done due to the kinetic friction. At point C, its potential energy is 0 and kinetic energy is 0 since they are at rest. Substitute. This other work done is negative since the kinetic friction reduces the energy of the body, the package. So this is negative. So M mass is 2. At point B, speed is 4. Force of friction is U sub K times the normal force, wherein this term is equal to 16. The normal force is equal to the weight, mg. So substitute. Mass is 2, g is 9.8, is distance is 3. Solving for U sub K in this equation. So U sub K is equal to 16 divided by 58.8. Coefficient of kinetic friction on this horizontal surface is equal to 0.27. Problem number 7. A 0.5 kilogram ball is tied to a string 2 meters long, and the other end of the string is tied to a rigid support. The ball is held straight out horizontally from the point of support with the string pulled taut and is then released. A. What is the speed of the ball at the lowest point of its motion? B. What is the tension in the string at this point? So from energy conservation principle, considering point 1 and point 2 for the motion of the ball. At point 1, its kinetic energy is 0 since it starts from rest. Its potential energy is weight times the height. This is the height, the radius, 2 meters. Its kinetic energy at point 2 is 1/2 mb sub 2 square, and its potential energy at point 2 is 0 since our reference level is point 2. So simplify, cancel out common factor, cancel out m. So the simplified form. Then solve for the speed at point 2. Extract the square root on both sides. Substitute z, negative 9.8, height negative 2. Then extract the square root. So the speed at point 2 is 6.26 meters per second. Letter B. What is the tension in the string at this point? So from Newton's second law of motion with our free body diagram, at point 2, The forces acting on the body is tension upward, weight downward, and its acceleration towards the center of the circle upward. So our equation, taking direction upward as positive and downward as negative, with the central acceleration equal to square of the speed divided by the radius. So T minus mg equals, the acceleration is positive, mv sub 2 square over r. Then solve for T and substitute the value of the mass, the speed at point 2, 6.26, and acceleration due to gravity 9.8. Simplify and combine. So the tension in the string at point 2 is equal to 14.7 newtons. Problem number 8. A 0.5 kilogram block attached to a spring with length 0.6 meter and force constant K equal to 40 newtons per meter is at rest at point A on a frictionless horizontal surface. A constant horizontal force F equal to 20 newtons is applied to the block and moves the block to the right along the surface. A. What is the speed of the block when it reaches point B, which is 0.25 meter to the right of point A? B. When the block reaches point B, the force F is suddenly removed. In the subsequent motion, how close does the block get to the wall? So this is our problem. Let us consider the motion of the block from point A to point B. So from energy conservation principle, the potential energy at point A is equal to 0. Kinetic energy at point A is 0 since it starts from rest. There is other work done on the block due to the applied force equal to 20 newtons. So work is equal to force times distance. At point B, it has elastic potential energy equal to 1/2 kx square at point B. Its kinetic at point B is 1/2 mv square. So substitute the value. Force is 20, distance is 0.25, K is 40, X is 0.25, M is 0.5. So in this equation, we are going to solve for the speed at point B. So simplify and solve for the speed at point B. So combine similar terms, divide both sides by 0.25, extract the square root on both sides, or the speed of the block at point B is 3.9 meters per second. Next, considering the motion of the block from point B to point C, because after the force is suddenly removed, it continues to move from point B to point C due to its momentum. So at point B, its elastic potential energy equal to 1/2 kx square. Its kinetic energy at point B is 1/2 mv square. At point C, its elastic potential energy is 1/2 kx maximum square. At point C, its kinetic energy is 0 since it is at rest at point C. So substitute the value. K is 40, X is 0.25 at point B. Then the speed at point B is 3.9, K is 40. In this equation, we will solve for the maximum X value. So simplify and combine. Solve for X. Divide and extract the square root on both sides. The maximum value of X is 0.5 meter. So the maximum value of X is 0.5, that is from point A to point C is 0.5 meter. Now let us consider the motion from point C to point D as the block moves back to the left due to the elastic potential energy. At point C, its elastic potential energy is equal to 1/2 kx maximum square. Its kinetic energy at point C is 0 since it stops for a while. At point D, its elastic potential energy is 1/2 kx squared, and its kinetic energy at point D, which it stops for a while, is equal to 0. So, substitute the value of k for t. Maximum value of x is 0.5. K is 40. So, we are going to solve for x in this equation. Simplifying and dividing both sides of the equation by 20 and extracting the square root on both sides, the value of x is 0.5 meter. This is 0.5 meter. Meaning, from point A towards the wall is 0.5. So, how close does the block get to the wall? So, it is the length of the spring, 0.6 meter minus 0.5 is equal to 0.1 meter. So, it's about 0.1 meter closer to the wall is the location of the block.